Yeah, good evening, everyone. Yes, even though today's participant number is very limited, I would like to start because there is no time to waste. And I would like one of you to be a co host so that you can manage the ones who are coming little later. Yes, Subhash, thank you. I'm making you as a co host. Yes, please take care of the latecomers. Yeah, with that, I would like to begin today's technical session. We have been seeing LSV for 3 weeks in a row now, and LSV-CV for 3 weeks in a row now. So, so to refresh the things that we have learned in past 3 weeks, I would like to summarize the things we learned very briefly. First of all, we saw what is LSV and what is CV. The only difference between LSV and CV is that in this case, we sweep the potential linearly from point 1 to point 2, which can be initial potential and vertex potential. In the case of CV, we reverse the potential back. So it is technically a cycle of sweeping. And we also saw why CV results in a peak-shaped voltammogram or a duck-shaped voltammogram when the reaction is completely limited by diffusion. And we also saw the influence of double layer thickness for the same. And later we went on to see the effect of scan rate on LSV, and particularly the peak current and peak position, and how it can be used to distinguish the nature of interaction of electroactive species with the electrode surface. And we saw the use of Rendell-Sevcik equation and the characteristics that are to be satisfied for a reversible reaction that is occurring via freely diffusing ion and adsorbed ion. And later we also saw the effect of reaction rate and the peak potential and peak current for a diffusion limited reaction. And then we saw another type of reaction commonly encountered in electrochemistry, that is quasi-reversible reaction. And we also saw the characteristic for a quasi-reversible reaction, and there is another type of reaction which is called irreversible reaction. And for irreversible reaction, we um saw that there are three instances where such an irreversible reaction can be observed. Instance one, where your product escapes out of the solution. Instance two, where your reduced or oxidized product in the forward scan is too stable to be reduced or oxidized back in the reverse scan. And there is a third case where the reduced or oxidized product during the forward scan is converting into some other product chemically, not electrochemically, so that the newly formed product, which is resulted from the chemical reaction, is not reducible or oxidizable back in the backward sweep. So these are the three cases where we see irreversible reaction. And also we saw how scan rate can be used to distinguish what is the case of irreversible reaction we are witnessing. In the case of irreversible reaction in which the product escapes out of the solution, like HER and OER, you will not see peak-shaped voltammogram. So the scan rate will literally not affect the maximum current density at your vertex potential. In the case of chemically uh, converting products into a different products, then which is not reducible or accessible in the for backward sweep cannot be detected at all. But if you vary the scan rate, you can see uh, the difference for reaction of a second type, where the reduced or oxidized product is too stable and it takes some time to oxidize back or reduce back. So if we reduce the scan rate, so we are giving enough time for the reduced product or the oxidized product formed in the forward sweep to get oxidized or reduced again, so that we can see a considerable amount of current density for backward sweep as well. So this is how we can use scan rate for distinguishing irreversible reactions. So that's what we have seen so far. And today we are going to see effect of IR drop on reversible reaction. So before seeing this, we should understand what is IR drop first. You should know where does it come from and how does it affect the voltammetric responses, and what are the contributing factors for IR drop. So IR drop, as the name suggests, it is a potential drop. We know I into R is equal to a potential as per Ohm's law, right? So it is potential drop that is occurring due to the resistance that is existing in all DC circuits. Okay, and in essence, in all circuits, irrespective of AC or DC, there is a resistance which is unavoidable or uncompensatable. So that is why this resistance is technically called uncompensated resistance, because you cannot compensate it. So, uh, so when we say about uncompensated resistance, it is not a resistance that is resulting from a single source. So people often confuse uncompensated resistance with solution resistance. In fact, solution resistance is the major contributor to uncompensated resistance, but solution compensation, I mean, solution resistance is not alone the sole contributor to uncompensated resistance. So, IR drop is not only from the solution resistance. You must understand this thing, because solution resistance is the major contributor, but it is not the only thing that is contributing to the overall resistance existing in the circuit. So, if you ask me the sources other than solution resistance where RU can get contributed, are the KIP and current collector, heterojunction, current collector, crocodile clip heterojunction, and all the heterojunction you have throughout the circuit. So each heterojunction has their own potential difference. Where there is a potential difference, there is always a resistance. So all this resistance can add up together and contribute to the higher uncompensated resistance. Okay, so including the solution resistance. So this is how the existing uncompensated resistance in a circuit is causing a potential drop. So this potential drop increases with increasing current. Okay, because obviously when the magnitude of I is higher, obviously your drop in potential is also going to be higher. So that is why for HER and OER at high over potential region, we see larger difference before and after IR drop compensation, because IR drop increases with increasing current density. So the second thing is that the electrode area. Okay, so your electrode may be having very less uncompensated resistance, but see, because your electrode is larger in surface area, it has a larger double layer. I mean, a larger double layer, which the double layer what we see here is just like a parallel plate condenser that we study in physics, which stores energy just through electrostatic attractions, not via charge transfer. So this is a fundamental difference. So the energy is stored just because of the ion absorption and desorption. So when we insert an electrode and apply a potential, the very first thing that happens in the electrolyte interface is that accumulation of charge and formation of double layer. And this process contributes to some amount of current, which is technically termed as non-Faraday current, because there is no charge transfer involved. So when your electrode is larger in surface area, okay, so obviously the capacitance due to the double layer, which is termed technically as double layer capacitance, is also going to be larger. So when the capacitance is larger, charging the capacitor, I mean the double layer, through the resistor which is already existing in your circuit, is going to take up some time. Okay, and that time will that time will let your interface not to feel or experience the actual potential what we are trying to apply. So there is always a potential drop because of this double layer capacitance at the interface. So both RU and double layer capacitance can cause potential drop and potential delay, so that there will be a shift in peak potential. So this is something we must understand. So overall IR drop is the major contributor in terms of peak shift, but in the case of larger electrode, double layer capacitance can also play a significant role, particularly when you increase the scan rate, because the scan rate always increases the double layer charging current, which means the capacitance also increases. So it will delay, and it will increase the potential delay felt by the interface. So we should be very careful about it too. So having seen this, we should understand one thing. So suppose if you see a CV feature such as this one, as you can see, with the increasing scan rate, the current is increasing, but we also see that peak potential is also increasing in the cathodic and anodic direction. So this is similar to that of what we have seen with the quasi-reversible reaction. Okay, but the only thing that will give us a hint that this is not a quasi-reversible reaction is that the peak-to-peak ratio, peak current ratio, IPC and IPA ratio will be equal to 1, which is a characteristic phenomena of reversible reaction. Okay, but a reversible reaction should not exhibits this phenomena, that is the increasing peak potential with increasing scan rate. So in that case, we need to compensate the IR drop like they have done here. But even then, at a higher, as I told you earlier, at a higher scan rate, charging of capacitor is also huge, so that it takes up a lot of time. So that the RC time constant is also high. Even after higher drop compensation, you will not see the exact position. I mean, the peak position, peak potential will not be constant. So because of high scan rate and the influence of double layer capacitance. So how can you avoid this issue? Actually, is that you can increase the supporting electrolyte concentration. So with the same concentration of supporting electrolyte, as you see here, after IR drop compensation, you will see the characteristics of a reversible reaction at only in lower scan rates, but at higher scan rates, it still looks like a quasi-reversible reaction. But if you increase the supporting electrolyte concentration, you can minimize the solution resistance contribution to the overall uncompensated resistance to a maximum extent, so that your IR drop will be minimum. And also you can perform IR drop compensation afterwards. You can by doing that, you can achieve better reversible characteristic in your CV, the increasing scan rate. So this is how you confirm that your CV is not of a quasi-reversible nature, but of a reversible reaction, but is being affected by both IR drop and double layer capacitance. Yes. And as I told earlier, CVs of CV and LSV of kinetically controlled irreversible reactions, such as gas evolution reaction, they don't show you any peak, and they are completely independent of scan rate. And there could be parasitic reaction of the catalyst or self-oxidation reduction reaction of a catalyst, which is also occurring along with the charge transfer controlled irreversible reaction. So this is a classic example where copper oxide is used for methanol oxidation reaction in alkali. Methanol oxidation in alkali is an irreversible reaction occurring via 6 electron 6 proton transfer. So with increasing scan rate, as you can see, the current density at the vertex potential is almost unchanged, but the copper oxidation and reduction peak is increasing with increasing scan rate. So within a single CV, we have both phenomena: the diffusion controlled catalyst oxidation, and here the charge controlled methanol oxidation. So this is how effect of scan rate can become handy in distinguishing the process that are occurring at the same time, the same interface in a given identical electrochemical condition. Yes. And as you all know, there are many applications because we have been discussing so many things now. So I don't want to go in there. Maybe, yeah, these things are known. Maybe this thing will be helpful for people, those who are working in biosensors. Yes, and supercapacitors. because diffusion coefficient is an important parameter in these two areas. You can design a better cell or a better sensor electrode for improving your limit of detection or improving your capacitance, amount of energy you can store via pseudo-capacitance. So how we do is that we use the Rendell-Selvig equation, but you should be very careful that the reaction what we study is reversible and satisfy the conditions required by the freely diffusing reversible reaction, and also obeys the Rendell-Selvig equation. So that is how we can use scan rate and cyclic voltammogram to find out diffusion coefficient. On the other hand, if you know the diffusion coefficient, you can also find out the concentration of the analyte, unknown concentration of the analyte in the solution. So that is how CV can be used extensively just by varying the scan rate and playing with other things within the solution and the electrode interface. Yes, that's all. So these are all unrelated. Yeah. Let me finish this here, and let's move on to yeah, the question and answer session. So yeah, so we have finished it today sharply in 15 minutes. Yeah, from next week I will move to other techniques, probably square wave voltammetry and differential pulse voltammetry. We'll see one by one, and followed by we'll have step potential voltammetry, single step, double step, and multiple step, and sample current voltammetry, so on. So every week we'll be seeing a technical. We'll be having a technical session in which I will be explaining the fundamentals and the ways of interpreting the data of a particular electroanalytical technique. So I would like to cover as many as many technique as possible, um, as soon as possible also. Okay, so with that I would stop here. So if you have any comments or questions or need clarification, you are welcome to ask. And uh, if you raise your hands, Mr. Subhas will make you as a host, then you can ask your question. Yes, and I think I have a question in the chat box. Yes, Sijil Damodaran, electrostatic charge storage and adsorption charge storage are same, right? Yes, they are same. Uh, and Sijib Das, in case of Tafel slope, we plot graph in terms of potential versus log current density, but the slope which is obtained has a unit of millivolt per decade. Yes. How can I get this? I'll explain it later. It is very easy because the Tafel slope is actually from 2.303 RT alpha enough. If you substitute the um, units of each of these constants, you will get this. And what is IR drop compensation? Can you explain once again? Yes, IR drop compensation is nothing but we are compensating the potential. You first understand what is IR. IR is nothing but potential. Okay, potential drop compensation. So we are compensating the potential which is dropped because of the existing resistance in the circuit. Okay, so because of this existing resistance, the quantity of potential or the exact potential which is felt by the interface is always lesser than what is actually applied. Okay, so this drop is what we call IR drop. To compensate for this one, what we do is we take the uncompensated resistance from impedance spectra and then multiply it with the current density at each experimental potential, and it results in a potential value which is nothing but the potential which is dropped because of the existing resistance in the circuit. So just by subtracting this drop potential from the experimental potential, you will get a new potential scale for the current density which is already recorded for each potential step, and that potential scale is called IR drop compensate potential scale. Okay, so that's how we do IR drop compensation. Why millivolt decade is used? We can use only millivolt, so where is the problem? Uh, no. Decade means this, as the unit suggests, that how much potential is required for your catalyst to jump from 1 to 10, 10 to 100. This is what we call decade, right, in logarithmic scale. So 0.1 to 1, 1 to 10, 10 to 100. So as the decades of current density increases, it is actually a measure how much potential is actually needed for your catalyst to increase the current density from by an order of magnitude. You see, so that's why we need to use the decade. You can simply use millivolt, and that is what your over potential is. So that is the basic difference between tuffle slope and normal over potential. Yes, thank you. And Miss Shetty, yeah, if you are a host now, you can go. Subhash, could you please make a Subhash? Yeah, Miss Shetty, you are a host now. You can unmute yourself and ask your question. If she is in there, you can make your question, Subhash. Yeah, yeah. Yes, no problem, Miss Shetty. Take your time. Yeah. Yes. Could you make a Mr. Andrew? Yeah, Andrew, you are a host now. You can ask your question.
Hello?
Yeah.
Can you hear me?
Yes, yes.
Yeah, thank you so much for taking all your time always for this wonderful discussion.
Yes.
We have just talked about IR drop compensation. What are the methods, the best methods that one can easily, measure the IR drop? Is there any best methods to be used for measuring the IR drop?
Um, Actually, we are not measuring IR drop anywhere. We are actually performing IR drop correction. To perform this correction, we need to know how much potential is actually dropped. I mean, how much IR drop is witnessed at each potential step. So to do that, what we do is we take the uncompensated resistance from the impedance spectroscopy, the very first point of your impedance plot, Nyquist plot, and multiply that resistance value at each the current density recorded at each potential step of your voltammogram, and that will result in a potential value. Okay, that is what the IR drop, I mean the potential drop. This has to be subtracted from the actual potential scale what we applied. So this is called IR drop. Okay, and the best method doing this for doing this is doing it manually, just as I explained. Of course, there are electrochemical workstation which can perform this during the measurement of the reaction, but I found that it is not a quite good method because when I tried to differentiate the activity differences between the manually IR drop compensated voltammograms and the electrochemical workstation compensated voltammogram, there is a huge difference in activity, and that is something I could not understand why it is happening. Then I understood that the resistance value what we set in the electrochemical workstation, it is actually treated as an absolute value, which means that the electrochemical workstation will vary the potential applied and the current what is recorded depending on the changing resistance during the reaction, in order to maintain the set resistance to be the same absolute value. And I am not sure how much true is this one, because I happen to know this thing from a vendor who used to sell electrochemical workstation when I was back in Sikri. But I'm not very sure about this fact. But I would suggest you to stick with manual IR drop compensation. Okay, and yeah, if you are not having any, we can move on.
Okay, thank you so much. Thank you.
Yeah, welcome, Andrew. Yes,
Yeah.
yeah, Mr. Tamil Saravanan.
Can you hear me now?
Yeah, yeah,
Can
sure,
you hear
sure.
me?
Yes, yes.
I have three questions regarding your previous paper, and that is a pitfall of using potentiodynamics
Okay.
in SS energy letters.
Yes.
Actually, it is a little bit technical also.
Yes.
Uh, the first question is actually about the current and exchange current density.
Hmm.
How we should get the correct exchange current density? One, I'll finish my questions and then you will answer wisely.
Okay.
And then the second is you quoted some paper, Shinagwa or something like that, and they are splitting the theta values as four theta values
Uh,
in the triple polarization.
yes. Yes.
Theta 1, theta 2, theta 3, theta 4.
Yes.
My question is actually we can split up even more. It's because it is actually like a wave form of thing, so we can apply in the mathematical wave form of mathematical equations. So how it will be standardized? Even you are suggesting that the over potential is also not giving a correct values. And my third question is, what is exactly onset potential? Each one having their own opinions. So these are all the things.
Yes. I forgot your first question, so I will answer from the back. The
J
first,
naught, which is
yeah.
J naught.
Ah,
Yeah, exchange current.
I remember now. Yes. Let's first start with onset potential. Onset potential, according to the recent IUPAC convention, it is the potential where your catalyst is able to deliver 1 milliampere per centimeter square in the catalytic turnover region. Okay, it is not the potential where it starts to bend or somewhere else. The recent convention says that the catalyst which is able to deliver 1 milliampere per centimeter square at a given potential, and that potential should be considered as its onset potential. Okay, but for cases where the current density is very low, for example, two electron oxygen reduction reaction, and also there is two electron water oxidation reaction, CO2 reduction reaction. In those cases, observing 3 to 4 milliampere per centimeter square is also a hard task. In that case, you cannot consider uh, 1 milliampere, the over potential at 1 milliampere per centimeter square to be your onset potential. I have answered a similar question in one of my previous sessions. So it is to be decided at your own discretion. So there is no one to tell you literally. So it depends on what reaction you are working with, and uh, how much is the current density that catalyst what you are working with is generating. So that is how you can tackle this issue. Secondly, about the theta value. So may I ask, what do you think exactly about this theta? What do you think what they are? So it
Actually, that is confirming the rate determining step in the hydrogen evolution reaction. They have split it into some mathematical equations like
yes, yes,
uh,
those
they were given into that
yeah, yeah,
formula.
yeah, I think you probably understood it wrongly. And the theta here, what they mentioned is nothing but the surface coverage. Okay, surface coverage of the active intermediate, which is limiting that particular reaction. For HER and OER, there are more. In the case of HER, there are 3 elementary steps, and in the case of OER, there are 4 to 6 elementary steps. In each elementary steps, you will be having a particular intermediate adsorbed on the catalytic surface. Okay, so they have, in the case of OER, for single electron mechanism, what they have chosen as a model, there are 5 elementary steps. So for each step, there is an individual intermediate which is to be assumed as the rate determining step. So the coverage of that intermediate is mentioned as theta 1, theta 2, theta 3, theta 4, and theta 5. Okay, so please don't
Yeah,
confuse
yeah.
this mathematics expression. So this mostly in electrochemistry, theta means it is surface coverage of an intermediate or the product or the chemisorb layer or adsorbed layer or under potentially deposited layer. So whenever you see theta in somewhere in electrochemistry text, it means mainly the surface coverage. Okay, so don't confuse this thing with the mathematical relationship. And what they try to say is that when the rate determining step changes, the surface coverage also changes. People, what people usually do is that in order to apply the BV theory, Butler-Bowman theory for TAFL analysis, and to make precise measurements of TAFL slope and exchange current density, the surface coverage of the intermediate in the rate determining step should be either 0 or equal to 1. Okay. So this condition can be met only at steady state. Please remember this. The surface coverage of an active intermediate of a rate determining step of an RDS should be equal to either 0 or 1. Only in these two conditions we can apply the Butler-Volmer equation and the Tafel equation. Okay, so this condition is met only when your potential and the current response which is recorded are at a steady state. But what is happening in CV and LSV is that the potential is fleeting and the current response what we are observing is also dynamic. It is not of a steady state response. So that is why they mentioned that with increasing over potential, the surface coverage of each intermediate when they are the rate determining step, that is also varying between 0 to 1, which means that we cannot arbitrarily take the LSV, which is recorded at particular scan rate, and correct. Even if we correct it for 100% IR compensation, the surface coverage will never be equal to 1 or 0. So it will be intermediate. In this condition, it is not correct to apply BV equation and also Tafel equation to find out Tafel parameters. Okay, that is the reason why we argued in my paper, which you have highlighted, that only steady state responses should be used for Tafel analysis. Okay.
Oh, yeah, understand that now.
Okay. And
And then exchange current density.
yes, exchange current density.
How
Yeah,
do we exactly calculating that?
yes. If you see the Tafel equation, the intercept A, you know what are the terms inside this A? It is intercept is equal to 2.303 RT alpha NF, right?
Yeah.
So
Yeah.
you need alpha NF and log J0, right?
Yes.
So
Yes.
log J0 should be on the other side of the equation. You should take everything out to the
Yeah.
intercept side. So you will have intercept multiplied by alpha NF divided by 2.303 RT. This is nothing but log J0 value. So once you solve this equation, you will get a value for log J0. So after that, you should take an anti-log of the same and you will get your exchange current density. And that is how you should calculate your exchange current density.
I thought that it is some form of extrapolation in the Tafel plot or something like that. You are just kept it into zero.
Yeah.
The potential value is zero, and that you just extrapolated it to somewhat range, and it will give you some value. Even the theoretical value and that extrapolation value were same or something like that. I don't know actually.
No. So just by extrapolating, you will get the intercept. So how else you will get the intercept then? So unless you extrapolate the Tafel line, from the Tafel region to the zero over potential mark, okay, and you cannot get the intercept. So the first step is in getting the intercept by extrapolating the Tafel line. So after getting the intercept, you should multiply the intercept with alpha n f, the Faraday constant, and divided by 2.303 RT. Okay, then this will give you log J0, and you should take anti-log of the same.
Anti-log token we can get it the first formula actually. So that is the major question I have.
Okay.
And which is very interesting, and the paper was very informative.
Thank you.
And we can get many. We have to put the papers after this paper because it gives some clear references also. Even the LSV peaks and the over potential thing, even in our lab, we have also the same kind of misleading thing.
Yes,
Even if you are just a little bit of change, it will change everything. Even that is, how can I say, the cyclic parameters, everything can change by changing the over potential thing. So there should be another way like this of papers. And my final question is, what is the solution to all of these things? You suggested that some galvanostatic things are going to be very useful to concluding these things, but I don't really buy it actually. What is you exactly tell to this world?
Yes, what I'm trying to say to this world is that all the electrocatalysts, whatever we are working with now for publishing our work are being characterized by transient techniques, CV, LSV, and other techniques. And we use some chronoamperometry or chronopotentiometry only to show their endurance. But in practical cases, when you suppose, let's assume that we have developed a great catalyst. So you are going to make a cell, full cell out of it. So will you be cycling the catalyst in the full cell? No, of course not.
No.
You will be asking the catalyst to perform a particular reaction at a set potential. I mean, more precisely at a cell constant cell voltage or a constant current density for the whole cell, which means that your catalyst is going to operate under steady state condition. So you must also determine the activity using a steady state technique in the transient technique, because the activity determined using transient technique and steady state technique will be very different. That should be that too. The difference is highly pronounced when the over potential increases further and further from the reversible potential of that particular reaction. So the very first thing what we can do is to perform the study in a steady state. But when we talk about steady state, there is also two different things. We can do it in galvanostatic mode as well as potentiostatic mode. But in the case of potentiostatic mode, where what we try to do is that we try to apply and control the potential of an interface, which is practically impossible because of the IR drop issue and the double layer capacitance issue. Because the IR drop and double layer capacitance, they always cause some potential drop in the interface. So we cannot control the potential at the interface. That is the reality. Okay. What we can do is that we can apply constant current. Instead, we can just observe the potential at the interface instead of controlling it. In that case, we don't have to worry about the IR drop issue. So you know the amount of current being applied, and your interface is responding you in terms of potential. So that is what the real capability of your interface. And in my opinion, everyone should characterize their material using chronopotentiometry.
Yeah.
Yes. And
I think that the more often papers are come by potentiostatic things only, but you have to lend a way to that. You have to put a paper on regarding that. Then only we can follow
it
it.
is underway. It is underway, and it will get accepted very soon.
Okay. Now that's very informative. Now,
Yes.
thank you.
Yeah.
Thank
Thank
you
you,
so much.
Sir. Yeah. Ms. Shetty, if you are ready now, you can ask your question.
Yes, sir. Am I audible?
Yes.
Sir, basically, I have very firstly, very good evening, and I have 5 questions, sir.
Okay.
The
Yeah.
first question is, when I run CV using copper as a working electrode as well as the counter, I found discoloration of counter. I couldn't find the reason for that.
Okay. What is the
Basically, I ran
medium? Yeah. What is the medium you are working? The
one
pH.
molar, yeah, 1 molar
Oh,
KOH.
okay. That is fairly enough to cause dissolution. Your count working electrode is copper, made of copper.
Yes, copper foam.
Yeah. So your counter electrode is
Copper.
what?
Copper again. Copper.
Oh, okay.
Both are
Okay.
same.
Okay.
But
Okay.
I have maintained the area higher, and this is where the working area is 1 by 1, and counter area is 5 by 1.
Oh, so you are observing discoloration in counter.
Yes.
That is because of the deposition of copper oxide that is dissolving out of your working electrode and depositing on the counter electrode. Have you done XPS on the counter electrode?
No, sir. No, not yet, sir. I found
Yes.
the discoloration, so I couldn't understand that.
Yeah, it is very common because I have been working with copper anodization for a while now, and I also use both counter and working electrode as copper, and I see this thing in 1 molar KOH. Yes, and I know that it is because of copper deposition.
Okay, so it will not cause any problem
No,
in
no,
our.
no, no. As long as you have both copper at both end. Yes.
Oh, okay. So my second question is, I have run LSB once, just to try, just giving a trial. But when I ran this LSB, I observed HCR both in counter as well as working. Then again, the discoloration of counter and working happens. and it
No, no.
goes back to its
You observed what
hydrogen evolution reaction.
at the same time at both
Yeah.
electrode? No, 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 no.
Yes.
Yes. How do you know both are hydrogen evolution reaction?
Uh, I assumed it, sir. I'm sorry.
So
It's
okay, you saw gas bubbles forming on both electrodes.
yes, yes, yes.
Yes. In that case, the one is oxygen and another one is hydrogen. And you could have also noticed this thing. One, the gas bubble, the amount of gas bubble formed at one electrode might be higher in quantity than the other.
Yes, yes, sir. Yes, sir.
Yes.
Yes.
Yes. The one with the higher quantity of gas bubbles is actually the HER electrode. And the one with the lesser amount of gas bubble is the oxygen electrode. So the oxygen electrode usually uh, dissolves copper into the solution and which gets deposited on the hydrogen evolving electrode. Yes,
Okay.
that is what happening.
Okay. So I
Yes.
have one more question. It might sound silly to you, but I'm sorry.
No, 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 no. There is nothing silly here. So this forum is for everyone. So anyone can ask anything from electrochemistry that can be from the primary level to the advanced level. As long as I know the answer, I'll be happy to answer. So never say silly or any other thing. Please go.
Okay, sir. I'm starting to do LSV right now. So
Hmm.
I just gave a trial, and I want to know, so stability study people try and give that first trial and after 1,000 cycle. Is it the 1,000 cycles of LSV or CV?
Uh, It is usually CV because I don't know any electrochemical workstation which can perform LSV continuously like we can do CV. What people usually do is that they perform an LSV and they put another CV experiment for 1,000 cycle and they also perform another LSV after 1,000 cycles of CV.
Okay,
So this is
okay,
how they take the LSVs before and after 1,000 CV cycles
okay,
to show the stability. But in my
okay,
opinion, doing stability using CV or LSV, both are useless and meaningless.
okay. So then,
Yes.
how can you claim that your material is? I mean, this is stable, or how can
Yes.
you?
Yes. You have chronoamperometry, chronopotentiometry, run it for days and days. You can show that from there.
Okay, sir. But in CA, I mean, in chronoamperometry or chronopotentiometry, you will be giving current and potential both. If it is chronopotentiometry.
In chronopotentiometry, what we do is that we supply a
Mm,
particular current density and we monitor the potential with respect to time. In chronoamperometry, we apply a potential and we
mm,
monitor the response of the interface in terms of current with respect to time. So these are the difference between CA and CP.
uh,
But the important thing is that we are letting the system to sit on a particular potential or a current for a very long time. So it is actually the true stability. Whatever we see with LSV, CV, 1,000 cycles, that doesn't matter. For example, if a material is undergoing corrosion phenomena and dissolution, redeposition, uh, even the 10,000 cycle won't even affect its LSV characteristic as long as it dissolves and redeposit. So it can go on and on. So there is really nothing we can say for an electrocatalyst which is to be used under steady state condition from CV. It is this much stable and that much stable. This is too much stable. So that is simply meaningless. So if you are working with the steady electrocatalyst, which is ultimately to be used in a steady state operation, you should always say how many hours or how many days of operation your catalyst can withstand at a particular current density or a potential. So that is what the most important aspect.
okay, sir. I'll try this and I'll get back to you next week.
Yes, yes,
Sir, I
please.
have one more question. Sir, I
Yes.
have tried LSV and I observed that first I initially started from +1 to -1 volt.
Mm,
Then I gradually increased the potential by point 0.2, like 1 to 1.2, then 1 to 1.4,
mm,
something like that. When
mm,
I went to 1 to 1 -1.8 volt,
mm,
it was like I was getting a decreasing potential. I mean, decrease in the curve. The curve was going down.
mm,
And suddenly, after 1.8 volt, it
mm,
started increasing again.
mm.
What does that mean, sir? I couldn't
Yeah. So
understand.
your working electrode is what? Copper again,
Yes, sir. Yes, sir.
and that is copper hydroxide reduction. So let me show you a slide. Just a moment.
Yes.
Yes. So in which medium you are working?
So I mean, yes, sir, 1 molar KH, sir. Everything I tried in 1 molar KH.
Okay. What is the reference electrode?
Reference AgCl, sir.
Do not use AgCl because there are a lot of issues with using AgCl. So something like this, right?
Yes, sir. I've come across this in your
Yes.
one of your papers.
Yes. Yes. So this is not 1.8. So if you see 1.8, around 1.8, it is probably the hydrogen evolution reaction, but that will not go up again. So that could be something else. And I suspect that either your reference should not be perfectly working because in alkaline medium, you should never use AgCl because I told this reason uh, in my very first session because in alkaline condition, the electrolyte what we have is K plus and OH minus, right? So
Yes.
when we insert AgCl electrode, which is filled with usually either saturated potassium chloride or 1 molar potassium chloride or even 3 molar potassium chloride, so we have a different anion in the reference electrode chamber, right? So
Yes, sir.
in the reference electrode chamber, we have Cl minus. In the electrolyte, we have OH minus. The ionic radii, electronegativity, and these are all and transport number. All these are different for both OH minus and Cl minus. So when these differences occur, there occurs potential gradient at the interface of the tip of the reference electrode and the solution, electrolyte solution in your cell. So because of this potential difference, there occurs resistance, and this resistance and the liquid junction potential can alter your reference electrode potential. But this is not what is causing the huge disturbance in your, what I can say, in your measurements. For a single LSV or CV, or for a limited time of use, using AgCl will not bother you much with the accuracy of your measurement. But when you use it for a very long time, I mean for hours and hours, what happens is that we know where there is a liquid junction potential and where there is a concentration different. So inside the reference electrode compartment, you have very high concentration of chlorine. So outside the compartment in the solution, you have very high concentration of OH minus, and the pH of potassium chloride inside your reference electrode compartment is nearly 7, but outside it is 14. So this pH difference also indicates that there is a difference in concentration of proton. So we know where there is a difference in concentration of proton, there occurs osmosis, right? So
Yes.
we know this. Yes, the higher concentration ions from higher concentration compartment will tend to diffuse to the lower concentration compartment. So over the time, the pH of the reference electrode chamber changes and pH of the electrolyte chamber also changes. So this causes huge disturbance in the potential scale because we know that from Nernst equation, the potential is dependent on the pH, right?
Yes,
Concentration
sir.
of ions. So you must not do that. Always use HgHgO reference electrode for alkaline medium and Hg2SO4 electrode for acidic medium. Use Calomel or AgCl only for neutral and near neutral medium. If you ask me, the best pH range to use AgCl and Calomel electrode is that from pH 6 to 8.9, there is no issue, big issue in using AgCl and Calomel. But beyond this potential, you should be very careful in choosing your reference electrode.
Sir, I get your point, but HGO is around 50,000, which is
Yes,
not
I know
affordable.
that.
So, what can be a
Yes,
solution for this?
you can make HgO, right? You know, it is very easy.
Okay, sir, I'll
Yes,
try.
yeah, yeah. You can find, you can buy HgO powder and Hg, and you can make the paste required for electrode preparation, and you don't have to use platinum wire for contact. You can use silver wire, no problem. But making HgO is also a difficult task. You will not get the potential stable for a while, and you should let your electrode achieve a steady state or an equilibrium state to have an established potential and changing potential. So there are these things. But I'm sure, very sure, your supervisor would be able to buy you a HGHO reference electrode.
Okay, sir. So, okay. So my last question to you will be, if you are running impedance,
Hmm.
uh, is it necessary that you should run open circuit voltage before running the this one EAS spectra, or is it okay to run at 0 volt?
Okay. So this has become a kind of a repetitive question, but it is okay. I will answer it. It depends on what application you are working with. Suppose, for example, if you are working for corrosion application, so you want to protect a surface or a coating or a metal from corroding, it is obviously that you should perform your EAS at OCV. Suppose if you work at a battery material or a supercapacitor material, and you want to know the E-car and I-car, the corrosion of your electrode material at 0 volt against the other half cell, you should set the potential of 0 volt against the other half cell as a reference to check the I-car, I mean corrosion current and potential of corrosion, E-car. So if you are working with an application where a catalyst is used, and on that catalyst charge transfer is occurring, you should always select a potential at which the particular reaction what we are studying is occurring. Okay, for example, if you are working on OER, you should always set a potential where OER is actually occurring. You don't have to set a potential 0 volt versus OCV or 0 volt versus reference electrode or OCV as the potential of your operation. You should be very careful in choosing this one, because I have published paper on this very particular topic, because from my experience of reviewing many papers in this area, I found that people are so confused about where to perform their EAS experiment. And I published this paper in Chem Electrochem. I'll send that paper to your supervisor. He will share it with you.
Okay, sure, sure.
Yes. Yeah, you can go through that paper if you still have any doubts, and you can always ask me in the next session.
Sure, sir. Thank
Yes.
you, sir, and congratulations for your uh, you being selected as the editorial board
Yeah.
member in Pleasant Journal.
Yes. Thank you. Thank you.
Thank you, sir. Thank you, sir. Thank you.
Yeah. So yes, in chat box we have Kurandevel Loganathan. If time permits, can you show application of iron drop with? Yeah, I'll do that next week, Kurandevel Loganathan. Yeah, because today we have no time. And Joe Blessing, what's the order of electrochemical workstation for HCR? Is it LSV, CV, and chronometric, or other way? Should I do for anything for oxidation? There is no specific order. You can use LSV or CV for preliminary characterization, for preliminary characterization, but you should not use the data what you obtain from LSV or CV for portraying your activity. That is what I mean to say is that you should not use the data of LSV or CV to say that this is the activity of your catalyst, okay, which is not correct, because those are transient response and they are always overestimated. So LSV CV can be used for preliminary characterization, but always steady state response, like multiple step potential voltammetry, like the SCV, sample current voltammetry I recently published, should be used, because those are having very close values when compared to the steady state responses, longer performed for longer time. Okay, so there is no specific order actually. You can do it in any order. But the very first thing you can do is simply running as LSV and see at which potential your material is able to catalyze the reaction and how much current density it could approximately give. So when you do steady state studies, so that is how you go with that. Mr. Paraj Chavan, can we have a lecture on career opportunity in this area, please? Yes, yeah, I have been encountering this question for a while now. I am actually trying to arrange a session, but because of this recent Russia and Ukraine issue, many of my collaborators are very busy in helping the students, those who are stranded in the war zone. And I was keeping a colleague of mine in my mind, because he can be the best fit to give such a career lecture. But he's very busy, very currently. Very busy right now in helping the students in Ukraine and those who are migrating from Ukraine to Poland and other countries nearby on the eastern side of Ukraine now. Yeah, we'll but soon arrange such a talk in the upcoming sessions. And Andrew, yeah, congratulations. Yeah, thank you very much, Andrew. Yes. And if we don't have any other comments, I would like to know what are the other techniques you would immediately want to learn, because I have chosen an order. I'm um, going to talk about square wave voltammetry and DPV for the upcoming 2 or 3 sessions. But if you people want something immediate or some other technique of particular interest, you can also say it to me, so that I will be happy to present them as well when time permits. So yeah. Yeah, so we still have 4 minutes. If you have any questions, you can ask me. Otherwise, we can conclude the meeting earlier too. There is no issue. And thank you for joining me today too. And I will upload this recorded session tomorrow on YouTube. You can always watch the discussion again. And yeah, let's meet again on the next Saturday. Probably we'll start with DPV as the technical session, and we will build on further based on the discussion what we'll have after DPV. Yes, thank you for joining. If you are done, you can leave.